want to explore a few alternative approaches to what could a player character in a 2D space game look like. You probably already saw some concepts where we have a planet with some kind of spaceship moving around it, trying to protect it from asteroids and aliens. What if instead of a planet we have a big robot body, and instead of a spaceship we have different attachments, arms and weapons that serve different functions and have different attacks? The game could have some kind of a progression system where we defeat enemies, collect their spare parts and use those to improve the abilities of our robot, growing more and more arms that give us new special attacks and power-ups. The character we are bringing to life today is a basic sentry reconnaissance robot. It has a special radar dish arm attachment that allows it to see hidden enemies, and it automatically scans its surroundings with its massive camera lens eye. I will program the eye to follow mouse cursor, but it can easily be adjusted to follow the nearest enemy, the fastest moving object, or, for example, only enemies of specific types. What if the radar dish allows us to uncloak hidden enemies, and then the eye will follow them around and track them for us? There are many game design opportunities here. Let me show you how to animate a player character and how to give it an interactive moving eye. Once we understand this technique, we can attach these moving eyes to enemies as well. I used this technique for an experimental creative coding project long time ago. Let's explore how it can be improved and used in games. I will also show you how to make the character patrol around the screen in different repeating movement patterns and how to optimize that code for performance. What other special abilities could a player character have? Laser arm? How about a hatch that releases a swarm of smaller robots? Give me your game design ideas in the comment section below. We are using images, so all the code will be inside Load Event Listener to make sure the code runs only after all the art assets are loaded and available. We set up our canvas using the usual 4 lines of code. I will set it to 600 x 800 pixels so that I can have the project and the code side by side like this, but feel free to make the canvas larger when we finish the project. I will provide some larger background images for you to download in the resources section below if you want a larger game area. I will have a class called Robot. Since the robot will be automatically moving around canvas in a movement pattern we will specify, I need it to always be aware of the width and height of canvas area. It needs to know when it moved off screen. Constructor will take canvas from line 2 as an argument, and inside we convert it to a class property to keep our code clean and modular. The robot will start from the middle of the screen horizontally and vertically. So I use this.canvas property to access width and height properties of canvas we set to 600 x 800 on lines 4 and 5. The robot will be kind of circular, so for now, let's give that circle a radius of 80 pixels. I give it a draw method. Again, we are keeping our code modular, so instead of pulling CTX variable from line 3 directly into my class, I will convert it to context argument and use that in here. We will connect this context variable with this CTX variable a bit later when we call draw method. I will show you. At first, I want to show you the eye rotation technique on a simple set of 3 circles to explain exactly how it works, and then we will attach images to it. To draw a circle on canvas, we have to start by calling beginPath method to tell JavaScript we want to start drawing a new shape. I use built-in arc method and this.x, this.y coordinates for the center point, radius of 80 pixels as we defined, start angle 0, and end angle math.pi times 2 in radians to give us a full circle. Then we call stroke to actually draw that path. We have the robot class, a blueprint to create robot objects. Let's create an instance of it. I create a custom variable, I call for example robot, and it will be equal to new robot, like this. On line 8, I can see that it expects canvas as an argument, so I pass it canvas from line 2. The new keyword triggered class constructor. It created one new blank JavaScript object for us, and it assigned it values and properties as we defined in the blueprint here. That means it has access to draw method we defined on line 14, so I call it. I can see it expects context as an argument, so I pass it ctx from line 3. By default, lines on canvas are black and 1 pixel wide. I can override those default canvas properties up here. We are drawing our robot. So far it looks like a simple circle. This white circle will be the outer shell of the robot eye. It will be the body. Then we will draw moving eye 1 and moving eye 2. That will track some moving objects, for example a mouse cursor. I copy this code to draw a circle and we will use it to draw eye 1. It will have a smaller radius, maybe just 70% of the main body, or 50%, maybe 0.6. We copy this and radius 0.3. Okay, so we have a robot that looks like a simple eye made out of 3 circles. I want to capture mouse coordinates and save them as properties on the robot class. It will be a simple object with x and y property. Now I can take this.canvas from line 11 and I attach event listener to it. We will listen for mouse move event. I have to use ES6 arrow function to make sure this keyword inside this event listener points to this robot object. Inside the callback function, I will just console log this auto-generated event object. As I move my mouse over canvas, mouse move event keeps triggering and mouse event object is being auto-generated. I want to know the coordinates of the mouse cursor. So we have this x and y position here, but since canvas is not full screen, we want to account for the space between canvas and the web page as well. We will use offset x and offset y properties instead. This will give us the correct position as we move over canvas. I assign them to x and y properties on the mouse object, so now, as we move mouse over canvas, we are constantly taking those coordinate values and making them available all across our codebase by assigning them to the custom mouse property here. Update method will run over and over to create some kind of movement. At first, let's test if everything we just did works by simply making the entire robot move with the mouse cursor. X and Y properties of the robot are equal to X and Y properties of the mouse. If I call update like this, it will run only once on the first page load. I want to call draw and update over and over to create animation. Custom function I call animate. Inside, I will draw robot, update its position, and I call built-in request animation frame method to draw and update it again and again. We pass it animate, the name of its parent function, to create a loop, and we trigger the first loop by calling animate here. It's leaving trails because by default, canvas is showing us old paint, the previous animation frames. If I only want to see the current animation frame, I call built-in clear rectangle method and I want to clear the entire canvas from coordinates 0, 0 to width and height to delete everything. Okay, so we are animating and we know we are correctly capturing mouse coordinates. Perfect. I delete this code. I want the eye just to hover around the middle of the screen and I want it to look towards the mouse and to follow it as I move the mouse around. We will be basically rotating these circles. A lot of the code in this game is based around the technique I'm about to show you. This is an extremely useful technique to know if you are interested in creative coding and in 2D game development. We have 2 points in a 2D space and we want to measure the angle in between them to know in which direction we want to push the eye, basically. We do that by first measuring dx, the distance between the center point of the eye and the mouse cursor on the horizontal x-axis. We calculate dy, the distance between them, on the vertical y-axis. With these 2 values, I can do 2 extremely useful things. I can pass them to math.hypotenuse method to calculate the distance between the 2 points. Or, in this case, I will pass them to math.atan2, which will give me the counterclockwise angle in radians between the positive x-axis and a line projected towards x and y coordinate of the second object. Which object is the center point and which one is the second object we are projecting the line towards depends on in which order I included them in the calculation of my dx and dy values. First of all, notice that with math.atan2 we have to pass it dy first and dx second. This is how this built-in method works. Second of all, we have two elements we are using to calculate dx and dy. These are the center point of the eye and the mouse cursor. Depending on if we used mouse or the eye first, it will change the layout of these angles when we pass them to math.atan2, but it doesn't really matter because it will always split angles into 4 quarters. We just need to be able to see, with the way we build the code, which direction is plus and minus. We can check that easily by using a console log. I will call this property this.angle because I want it to be available all over my robot class, not just inside this method. I created that property here on line 15 and initially I set it to 0. So now let's console log this angle to see the range of values that math.atan2 is returning. Because of the way I wrote this code, we get a set of values that start from 0 here. We are moving into positive values. These values are in radians, by the way. We move all the way to 3.14 plus pi, and then we immediately jump to minus pi. And as I keep moving this way, we are going back towards 0. Okay, so negative values are here, positive values are here. I will just make a quick note of these value ranges so I can work with them easily. Since math.atan2 is giving us these changing values as we circle around the eye, we always know where the mouse is in relation to the eye. We can use this angle value to move the eye towards the mouse now. We know the angle value goes from 0 into plus pi values, then from minus pi back to 0. Important thing to understand is that pi is around 3.14 radians, half a circle. Pi times 2 is a full circle, around 6.28 radians, or it can be converted into 360 degrees. Let's move the eye. This part will be the outer body of the eye. It will not move. I1 will move, and we will move it by changing its x and y coordinates. Horizontal x coordinate will be the center point of the eye, plus this angle value generated by math.atan2 passed to math.cosine. As we pass this change in angle value to math.cosine, it maps these values along a wave with value ranges between -1 and +1. We will explore this further in a minute. We have to do the same thing for vertical y coordinate, vertical center point of the eye, plus the same angle value, this time passed to math.sine. Sine will also map the change in angle value we are passing to it to a point somewhere on a sine wave between -1 and +1. If we pass sine and cosine the same angle value, they will work together to map that angle value somewhere around the radius of a circle. Let me show you. Because they map these values within such a small range of -1 and +1, the motion is barely visible, so we can multiply that range by a certain radius value to increase the size of the wave, basically. I can multiply it here by the radius value. And I do the same to the vertical y coordinate. Now I hope it's becoming more clear how sine and cosine are converting those angle values generated by math.atan2 to a position around the eye. When you play with these values, it will become more clear what is happening. I adjust the radius to a value that will make the eye circle move on the inner border of the outer body circle. It's trial and error, I guess, so I play with the code until I get there. 0.35 is good. You can swap sine and cosine, use both sine, both cosine. You can change the radius value to x and y separately, just to see how the movement reacts. Hopefully it will demonstrate very clearly what exactly is happening and how those angles we got by passing dx and dy to math.atan2 now help us to determine which direction from the center point of the eye we want to push the inner circles, so that the eye points towards the current position of the mouse. We can do the same thing to the smaller inner eye. I call it I2. Again, we account for cosine and sine value of that angle between the center point of the eye and the mouse cursor, and we multiply it by some radius, because by default these methods map values between a small range of -1 and +1. I want the eye to be on the inside, so definitely not this, although I might use this for some other feature, maybe. How about radius of 0.6? Yes, we have an eye that follows mouse cursor around. If we use position of enemy or some other object here inside dx and dy calculation, instead of using mouse position, this technique can be used to make the eye follow any object we want. I console log this.angle from inside mouse move event listener. So because we use mouse first and position of the center point of the eye as the second operand in these calculations, math.atan2 maps angles in this particular order. We start from 0 and we move into positive values. Here we are around 1.6 radians, which converts to roughly 90 degrees, quarter of a circle. If I keep moving this way, we reach 3.14. The value of pi, which is exactly half circle or 180 degrees. Immediately as we reach pi, it switches into minus pi and we go from minus values up until we reach 0 again. Because we used mouse first and center point of the eye second, when we move mouse around the eye, here are the plus values going in this direction and here are the minus values. We don't really care where these values are placed because we can always check like this and then adjust the code that comes after to work with these value ranges. Math.atan2 did its job and it's given us a set of distinct angle values as we move one object around another, and there are so many things we can do with this. I hope this clarified a bit how this works. Feel free to play with the values here and try to modify it and break it. When you observe how the animation reacts to the changes you are making, hopefully it will become clear what exactly is happening. Trigonometry is notoriously difficult. You don't have to understand all of it at this point. Just try to remember how to use it, and if you learn one thing here, try to remember that if you get dx and dy between 2 points and pass them to math.atan2, it will map angles around these objects to help us determine where they are in the 2D space in relation to each other. We will use this technique again for even more interesting things. We created a moving eye as a set of 3 simple circle shapes. Let's turn it into an animated interactive space robot. I'm giving you a lot of free game art with each class in this series. You can use it however you want for your own personal projects as well, if you want. You can download all project art assets in the resources section below. First we start with the body image. It's a scanner robot with a big radar dish arm. It can be used as the main player character in our game. We can give it more laser arms later. Or it can be used just as a helper scanner robot or as an enemy unit. Source will be body.png, alt is body, and ID will be body as well. I don't want to draw that image element, I just want to load the image in memory so that I can draw it with JavaScript on canvas a bit later. I create a div with a class of hidden. I set hidden to display none, so all images I put inside will be hidden automatically. Let's draw the body. Built-in drawImage method needs at least 3 arguments: the image we want to draw and x and y coordinates where to draw it. We can also pass it width and height to scale the image up and down, but a good practice is to use image files that are the right size. Pre-production and preparing your images in graphics editor before you use them is of course much more performance efficient than making JavaScript resize the images for you, although it's also possible. This series is all about performance improvement tips, so I will give you all the images optimized and at the right sizes, so we don't have to do any dynamic resizing with code. Circles are drawn from a center point, and rectangles and images on canvas are drawn from the top left corner. So if you want an image to be centered over a circle, you need to offset its position. Let's offset this horizontally by half of image width and vertically by half of image height. It would work if the robot was just a circle apart, but we have these wires and radars around it, so we need to account for some extra pixel values. Since the size of the image is static, I can hardcode these offset values here. Maybe plus 65 horizontally, vertically minus 50, 52, 53 pixels. Nice. Important thing is to include this.x and this.y in all these positioning calculations, because that way we will be able to move the entire robot and all its parts around the screen later. If this was a simpler character, I could have just colored the eye circles and it would look good, but we also have images for individual eye layers in this case. I remove the outer circle since we replaced it with an image. I bring 3 more images into the project. I1, I2, and reflection, which will be on top to give it even more polished look, I guess. We bring them into the JavaScript project as class properties. I call them I1 image, I2 image, and reflection image. Be careful about camel casing and capital letters here. I replace I1 with an image first. Image we want to draw is this.I1image property we just created, and x and y coordinates will be the same values we passed as x and y to the circle. I correct my spelling here. Again, I have to offset the position of the image by half of its width horizontally. And by the half of its height vertically. Yes, we can delete the circle as we replaced it with an image. I adjust the radius to make the edges match the new eye socket better. I can copy this code block and I use it to draw I2 image. Radius will be maybe 0.65. I delete the circle. Nice. We replace the circles with images and we have an interactive robot now. I copy this code block and I will use it to draw the reflection image over the eye, to seal the image in and to make the robot look even better. I get an error. Let's see. Right, I forgot to put the reflection image into my project folder, so I do it on my other screen. Nice, we are drawing reflection. I actually removed these offset values. We want it to be centered over the eye itself. So this is how you apply interactive moving eye to an in-game character. We can do so many more things with this now. Let me show you how I would improve this to really bring this to life. For example, instead of a static image, we can animate the whole body as a sprite sheet. I put together some motion and animations and I turn them into a ready-to-use sprite sheet for you. You can download it in the resources section below. I need to make sure I call it something else, for example body sprite, spelled like this. I bring it into the project here. I call it body sprite. I replace that here inside the draw image method, and now we are just drawing the entire massive sprite sheet at its original size, at these x and y coordinates. I need to know width and height of a single sprite frame. In this case, a single frame is 370 pixels wide, and height is 393 pixels. Down here, we are passing draw image method 3 arguments: image to draw, horizontal x coordinate, and vertical y coordinate where to draw that image. I will pass it also 4th and 5th arguments for width and height. Now we are squeezing the entire sprite sheet into the area of one frame. What I actually want is to go through the sprite sheet horizontally from frame to create animation. For that, I need to use the longest version of drawImage method, and I have to pass it 9 arguments. The image I want to draw, source X, source Y, source width, and source height of an area I want to crop out from the source sprite sheet, and destination X, destination Y, destination width, and destination height to specify where on destination canvas I want to draw that cropped out image onto. First, let's just crop out the left frame, so source X, source Y will be 0, 0, and source width, source height will be sprite width and sprite height. We are cropping out the left frame and drawing only that frame on canvas. I create a property called frameX for horizontal sprite sheet navigation, and max frame, it will hold the number of maximum horizontal frames. Source X argument will be frameX times sprite width. So when frameX is 0, we draw this frame. When frameX is 1, we draw this frame, 2, 3, 4, 5, and so on. Inside update method, here we handle angles. Here we will handle sprite animation. If frameX is more or equal to max frame, set frameX back to 0. Else, keep increasing frameX by 1 for every animation frame. And that's it. You can see I make the upper and lower shell move. Radar dish also moves up and down, and we have some cables swinging below. Some of the exhaust valves are also moving as they pump fluids and fuel through the robot's body. It's a very subtle set of animations, but it really makes our sentient space machine come to life, I think. I can also convert this code block into a single line by using ternary operator, the only JavaScript operator with 3 operands. The syntax is the condition to evaluate. If frameX is more or equal to max frame, if true, set frameX to 0. Else, keep increasing frameX by 1. So if this is true, question mark, do this, else, colon, do this. Ternary operator here is used as a simple single-line if-else statement. It's just a simplified syntax to do the same thing. We are still animating the sprite sheet by cycling through the horizontal frames. We can position the robot anywhere around the canvas by changing these values. Let's say it has some weapons to defend itself and enemies are coming from all sides. And we can upgrade the robot to give it more arms and more attacks. I think that would make an interesting game. Let's make the robot move around in repeating looping patterns. We can do that by changing its X and Y coordinates. If I increase this .y, robot will start moving down and it will move completely off screen. We talked about trigonometry and we learned that if we pass a change in angle value to math.sine or math.cosine methods, they will map these values along a wave shape. Let's say I have a movement angle and I increase it by 0.1 for every animation frame. I declare it as a property on the robot class. Initially, I set it to 0. I will rename it movement angle here and here. And I will set y to its current value plus sine of this movement angle value. We get this motion as the ever-increasing movement angle value gets mapped along a sine wave shape, because here it's connected to the vertical position of the robot. We know we can multiply that by a certain radius value to increase the range of the wave. This value will determine how fast we are going through the wave. I will just experiment with these values a bit to get a better understanding of how they affect the motion. I can see the motion is going towards the bottom side only, because I am using this .y here and here. Rather than updating the middle value, let's save it as a separate variable. Center X is this.x, so middle of canvas horizontally. Center Y is this.y, so middle of canvas vertically. Now I use center Y here to make sure the robot hovers around the middle of the screen. I guess I increase the radius, make it go faster, increase the range of movement even more. I copy this line of code and I do the same thing for this.y. If I combine cosine and sine, they will work together to give us a circular path. Why is it not centered? Just bear with me a second. I need to use center X here if I want this to be centered. Okay, so we are passing ever-increasing movement angle value to cosine and sine, and they map these values along a cosine wave and a sine wave shape. In combination, applied to x and y coordinates of the robot, it results in repeating a circular motion. As the robot body moves around, notice that the eye still stays focused on a specific point, in this case on the last known mouse location. I can define how far it moves left and right by this value and how far it moves up and down by this value. We can also create different movement patterns, not just circular. For example, if I make movement angle here go 3 times faster, it will go through 3 cycles before vertical movement does a single loop. So we get a movement pattern like this. If I use 0.5 here, it will go through 6 waves horizontally before it completes 1 loop vertically. You can play with these values and see what different motion patterns you can get. You can see how this can be used to make the robot patrol around the game area. I slow it down and I will console log this.angle. I actually want this movement angle. We have an ever-increasing number being passed to cosine and sine, and these methods are mapping those angle values on wave shapes. Even though it would take JavaScript a long time of increasing this number before it starts affecting performance of our codebase negatively, it's a good practice to manage our values and loop them rather than having a value that never stops growing, like we have here. The problem is I can't just reset it to 0 whenever I want. I say if movement angle is more than 5, set movement angle back to 0. You can see the robot gets reset halfway through the motion loop, all the way to the beginning. I want to reset this value at some point when the transition will be invisible and when it will result in a seamless, smooth motion. We have to understand that the robot moves in cycles. This angle value is in radians. Math.pi times 2 is approximately 6.28 radians or 360 degrees. That's one cycle. Because I make the vertical position cycle at half speed, I have to wait until we get to math.pi times 4, and at that point I reset to 0. This should give us a smooth transition. If we are moving very fast, we can also use remainder operator to account for some extra space we traveled before we managed to reset. I will console log the word reset to show when the reset happens. We reset now. Good, the transition wasn't noticeable. In console, I can see that we get to 12.6 radians, which is approximately math.pi times 4. And then we reset back to 0. If this was just times 1, we cycle back to the initial position every math.pi times 2, so I could adjust this reset condition. Basically, we just need to determine what is the angle size when we are back at the starting position, and at that point we reset back to 0 to get a seamless motion transition. I go back to this motion pattern and I slow it down. The eye just looks around to the sides, but if the mouse moves over the eye, we get this weird unnatural motion. When the mouse is too close and moving over the eye is no longer looking at it. Let's improve it and actually make it follow the mouse even when it's very close, like this. I create a property called eye1radius and I want to use it here. Basically, I wanted this part to be dynamic in certain circumstances. I don't want this value to always be the same. Initially, I1 radius will be this.radius times 0.4, same as it was before. And I use that variable here and here for x and y position of I1. If I change this value, we can move I1 around. Good. I do the same thing for I2. I2 radius variable will replace these hard-coded values, making the distance of I from the center point dynamic if we need it to be. I use that variable in x and y position calculation of I2 here and here. It all still works the same, but now if I give it different values, I1 and I2 move at different distances from the center point. I actually want them to move at 0.4 and 0.65 most of the time. Only when the mouse is closer to the eye, we will make these values smaller, and we need to make sure we keep the same ratio between them so that it still looks like an eye that is focusing on an object. 0, 0 will make the eye look directly forward. How do I make these values dynamic and react to mouse position appropriately? I will save the default distance we have here in separate variables called I1 distance and I2 distance. Now, if we modify I1 radius and I2 radius, we saved their default values and we can go back to them if we want to. I think I need to do it like this. Let's see. We already calculate dx and dy between mouse and center point of the eye. I can use them to get the actual distance between these 2 points, either by using Pythagoras theorem formula or even simpler with built-in JavaScript method called math.hypotenuse. I pass it dx and dy, this side and this side, and it will give me the size of hypotenuse, which in this case also represents the actual distance between these 2 points. So if mouse is outside the eye, use the default eye positioning to make the eye look at the mouse. If the mouse is inside the eye, we will use smaller values depending on the current distance between the center point of the eye and the mouse cursor. If distance is less or equal to I1 distance, I guess. Let's copy this code. Right. So if mouse is too close to the eye, that the eye needs to look inwards, we set I1 radius to distance times 0.4, and I2 is a distance times 0.65 to keep the same ratio between them and make it look natural, I guess. Perfect. Now it's following the mouse exactly in the way I want it. The threshold needs to be larger. I guess we want the radius of the outer shell, so not really I1 distance. I can use a set value here, or maybe I say times 2. Times 2.5. Probably it's better to use a hard-coded value here in this case. I need to test this a little bit to see what I just did. The way the eye follows the mouse, now it looks so much better. How about we give it 2 modes? At first, it's just randomly looking around, scanning the area, and when the mouse enters canvas, it will detect it, focus on it, and track it. I will give it a tracking light that will switch on when in tracking mode to make it visually distinct. I call it detector light. I bring it into the project here on line 27. I will draw it down here inside the draw method. I can copy this code block and use detector light image. I want to place it over the receiver wire, so I just offset its vertical coordinate. Like this. I will give it a new property I call, for example, tracking, and initially I set it to true. I want to draw the tracking light only if tracking is true, so I put this code block inside this if statement. Now we just handle it somewhere here. For example, I can do it inside mouse move event listener, or mouse enter event would also work. When mouse move is triggering, tracking is set to true. If mouse leaves canvas element, we set tracking to false. Okay, I enter canvas and move mouse around. Light goes on and eye tracks the position of mouse cursor. When I move the mouse outside of canvas, mouse leave event sets tracking to false and the light goes off. Perfect. The eye stays focused on the last known mouse location. Initially, I set tracking to false. Yes, that's even better. What if I wanted the eye to start scanning space around it even when it's not detecting anything, when tracking is false? I can do it here inside the update method. If this code block is true, we know we are tracking because mouse cursor is very close to the eye, so I can do an else if here, because we know these two conditions will never happen at the same time. Else if tracking is false, mouse is outside of canvas and we will be modifying eye position. We called it I1 radius and it will be I1 distance, the center eye position value, times cosine of the movement angle we are already using to move robot's body in repeating patterns. Yes, I1 is moving. Let's do the same thing for I2 radius property. I have to use both sine or both cosine, I guess, because I need I1 and I2 to move along the same path. When I enter, we are tracking. When mouse leaves canvas, the eye goes into autopilot and starts moving around automatically, just scanning the area. If I make this move, the tracking breaks. That's a bug. I can fix it, I guess, by refactoring this code block a bit. I think it should work like this. One big else if statement. Either mouse is very close to the eye, so we are adjusting I1 and I2 radius. Else we are still tracking, mouse is inside of canvas, but it's not inside the eye, so I can move around the radius of the eye socket, so we set I1 radius and I2 radius to the original distance values. Else, meaning we are not close to the eye and we are not tracking at all, meaning the mouse is outside of canvas, and in that case we want to use movement angle for a simple autopilot motion. What about we give it a laser arm with two modes, a basic laser beam and a super laser attack? Join me in the next part if you want to learn how to do that. Click the like please.